Welcome back to Pentagram Prime, everyone. If you want to watch another ski video, then you may need to wait a few months. Gotta say, I'm really happy to be talking over this image. For a while there, I didn't think I'd get this far. So today we will be using residue theorem to solve the integral of x to the a minus 1 over 1 plus x to the third from 0 to infinity. In this specific example, we will be evaluating the integral for values of a greater than 0 but less than 3. This problem is spelled out on page 302 of Marsden and Hoffman in exercise number 6, and I really wish that I had read the text a little more closely before attempting it. More on that later. My records indicate that I first started work on this thing on April 11th of 2023, and that I started a new job about 6 days later. Without giving away too many personal details, the job was in the food service industry, and I'm amazed that I can still do arithmetic after what this job frequently throws at me. As with other problems on the channel, we will be utilizing residue theorem in order to solve this integral. In short, the residue theorem basically states, details aside, that the contour integral of a closed path in the complex plane is equal to the multiple of 2 pi I times the sum of the residues inside of, though not located upon, the closed contour. Residues, generally speaking, don't exist without discontinuities or are equal to 0 otherwise. To that end, we need to determine where the integrand of our integral blows up when generalizing that function to the complex plane. For this reason, we will now turn f of x into f of z and study the properties of its denominator. The numerator z to the quantity a minus 1 has no discontinuities for our purposes, but feel free to have a look if you don't believe me. So we are interested in values of z in the complex plane where the quantity 1 plus z cubed is equal to 0. The result is the equation z cubed equals negative 1. For those unfamiliar with the deeper meanings of negative 1, then you can go back to real analysis. Those of you who enjoy scary places like the complex plane will quickly realize that negative 1 is equal to e exponent I times pi. This expression simplifies to the quantity z on the left-hand side when we raise both sides of the equation to the power of 1/3. But what do we do with the right-hand side? Fans of the channel probably know where I'm going with this. I've explained this before, but it never gets old because who wants to scroll through my videos looking for my methodology? If we let z equal the absolute value of r times e to the I theta, keeping in mind that both r and theta are real, then we can express the quantity of z to the power of 1 divided by n as the absolute value of r to the quantity 1 divided by n times e exponent I alpha. What is alpha, you ask? It's actually a largely imaginary concept created by people who thought they were engaging in scientific research when they took a bunch of captive wolves and subjected them to what I like to describe as a bad prison cliche. Then these same sick fucks projected their own personality traits upon a bunch of helpless animals. Oh, sorry, I'm just ripping on the alt-right. For our purposes, alpha has multiple values and is equal to theta plus 2 pi k quantity divided by n. The variable k takes on integer values from 0 to n minus 1. So for our purposes, z is equal to e exponent I times alpha, and I would hope that it's obvious that r, not shown, is equal to 1. Theta is equal to pi in this context, and k takes on values of 0, 1, and 2, since the value of n is equal to 3. This results in values of alpha equal to pi over 3, a value of pi, and 5 pi over 3. Keeping in mind that r is still 1, we can see that z takes on 3 values located on the unit circle when plotted in the complex plane: e exponent I pi over 3, e exponent I pi, and e exponent 5i pi over 3, or e exponent I 5 pi over 3, depending on how you like to write these things around. I apologize for the shoddy artwork. We came here to solve a real improper integral, and for that reason we will choose a path that includes the positive real axes. For the moment, I will ask that you take a leap of faith and trust me that a good choice for a closed contour is this slice of pi encompassing the singularity at e exponent I pi over 3. This contour forms a clockwise path about e exponent I pi over 3 and excludes the other two singularities. It has a radius of capital R, where R must be real and greater than 1. The angle between the real axes and the other straight line forming the pi slice is 2/3 pi. The reasoning behind the choice of 2 pi over 3 will be explained later. For now, let us supersize this slice of pi. We will be evaluating this path integral as 3 separate components, of course, and I find it helpful to label them. Starting on the real axes, we will denote the path from the origin to positive capital R as alpha. It is essentially the integral that we ultimately seek. However, the upper bound of integration has been substituted with capital R. The path of integration next moves onto an arc with a radius of capital R starting on the real axes and ending in the second quadrant at an angle of 2 pi over 3 or 120 degrees. Along this path, z is equal to capital R times e exponent I theta. We will refer to this curve as large or capital gamma. A straight line linking the end of the aforementioned arc to the origin closes up our contour, and this line will be referred to as little gamma. Along this path, z is equal to little r times e exponent 2I pi over 3. The variable little r changes from an initial value of capital R to a terminal value of 0 along the path of integration. But before we get to the fun that is evaluating the 3 contours that form our oversized slice of pi, we need to calculate the residue of e exponent I pi over 3. Fans of the channel should be familiar with proposition 412 on page 244 of Marsden and Hoffman. Before I dive in headfirst with calculation of a residue, I prefer to rigorously check to see that I'm using the proper methodology. Prop 412 has us separate the complex function f of z into functions g and h, representing the numerator and denominator respectively. This method requires that g of z naught be non-zero and that h prime of z naught be 0. Here f of z is z to the power of a minus 1 quantity divided by 1 plus z cubed. The result is that g of z is equal to z to the power of a minus 1 and h of z is equal to 1 plus z cubed. Calculation of h prime requires use of a complex derivative. H prime of z is ddz of 1 plus z cubed, and we get 0 plus 3z squared on the back end. Carrying out the required test on g at z naught equals e to the power of I pi over 3 gives us a non-zero value for the function. This is because there is no exponent that may be applied to the current value of z naught that will produce a 0 value. H prime of z naught also works out to a non-zero value, and the requirements for use of Prop 412 are satisfied. Calculation of the residue is pretty straightforward once we have g of z naught and h prime of z naught. Residue of f at z naught is equal to g of z naught divided by h prime of z naught, or the quantity e to the power of I pi over 3 to the power of a minus 1 divided by the quantity 3 times e to the power of 2I pi over 3. The exponential in the denominator can be pulled into the numerator via a sign change in the exponent. From here, we pull the 3 in the denominator to the front of the expression and combine the exponents of e. The I pi over 3 terms combine with the effect of canceling out a 3 in the exponent's denominator. We now have the expression 1/3 times e to the quantity I pi times the quantity a over 3 minus 1 for the residue of f at z naught. Why don't y'all put a pin in that while we solve some path integrals? Capital gamma. The starting point for the path integral capital gamma is 0 plus real uppercase R, located on the real axes. The path moves along a counterclockwise arc of radius uppercase R that ends at the point z equal to capital R times e to the power of 2I pi over 3, located in the second quadrant. As we travel along this path, z equals uppercase R times e to the power of I theta. Here, theta is the angle off of the positive real axes. Capital R remains constant along the path, and the only variable that changes is theta. So if we take the derivative of both sides of our expression for z along the path and multiply both sides by d theta, then we have an expression for dz in terms of capital R theta and d theta. Next, we substitute our expression for z in terms of capital R and theta into f of z. Since the only variable that changes along the path capital gamma is theta, our path integral becomes an integral with respect to theta alone. With the path integral capital gamma reduced to an integral over theta alone, we next apply the integral inequality. This states that the absolute value of an entire integral of a single variable is always less than or equal to an integral of the absolute value of the integrand taken over the same bounds of integration with the same variable. So if we take the absolute value of the integral of f of z over the path capital gamma, then we can state that it is less than or equal to the integral from 0 to 2 pi over 3 of the absolute value of our expression of f of z in terms of theta and capital R with respect to theta. With this integral in hand, we now focus on the integrand on the right-hand side. Utilizing some rules for absolute values, we can manipulate the integrand in question to our advantage. The I term in the numerator drops out immediately because it has an absolute value of 1. Next, we note that the absolute value of a quotient is equal to the absolute value of the numerator divided by the absolute value of the denominator. This allows us to separately deal with the absolute values of the numerator and denominator. Focusing on the numerator of the integrand in question, we find that we can pull the quantity capital R to the a outside of the absolute value because capital R is positive and real. The variable a is real, and thus the quantity capital R to the a is positive for all values of a considered in this exercise. The variables a and theta are real in the context of this problem, making the remaining absolute value of e to the ai theta equal to 1 for our purposes. This allows us to cross out the remaining absolute value in the numerator, leaving us with capital R to the a divided by the absolute value in the denominator. Our version of the integral inequality now becomes absolute value of the gamma path integral is less than or equal to r to the a divided by absolute value 1 plus capital R cubed times e to the 3I theta d theta from 0 to 2 pi over 3. Next, we apply the reverse integral inequality to the denominator on the right side of the inequality, and we use a double negative in order to match its form. Absolute value of 1 plus capital R cubed e to the 3I theta becomes greater than or equal to the absolute value of 1 minus the absolute value of negative capital R cubed e to the 3I theta, and boy oh boy is that a mouthful. From here, we manipulate the right side of the aforementioned inequality. We can separate the negative capital R cubed and e to the 3I theta terms because an absolute value of a product is equal to the product of the individual absolute values of those terms. The minus sign in front of capital R cubed disappears since the absolute value of a negative is a positive. Thus, our inequality is now absolute value of 1 plus capital R cubed e to the 3I theta greater than or equal to the absolute value of capital R cubed minus 1. In this context, capital R can be taken both as real and greater than 1. This makes the quantity capital R cubed minus 1 positive and allows us to shed those absolute value signs that I know you are getting tired of. I am. Now we can assert that the remaining absolute value on the left is greater than or equal to capital R cubed minus 1. If we take the reciprocal of both sides, then the direction of the inequality reverses. Both A and capital R have been established as positive and real. Thus, capital R to the power of A is positive, and we can multiply both sides of the current inequality without affecting the polarity. If we integrate both sides with respect to theta, bounds being 0 and 2 pi over 3, we see that the integrand on the right side of the inequality has no theta dependence. Solving the remaining integral is trivial, and the right side of the inequality is reduced to an expression of the variables capital R and A alone. We have thus shown that the integral with respect to theta of capital R to the power of A divided by the absolute value of 1 plus capital R cubed times e to the power of 3I theta from 0 to 2 pi over 3 is less than or equal to the value of 2 pi over 3 times capital R to the power of A divided by capital R cubed minus 1. A mouthful for sure, but I assure you there is a point. We have already shown that the aforementioned integral on the left side of the inequality is greater than or equal to the absolute value of the integral of f of t with respect to t along the path capital gamma in the complex plane. Combining these inequalities shows us that the aforementioned absolute value of the capital gamma integral is less than or equal to the value 2 pi over 3 times capital R to the power of A divided by capital R cubed minus 1. So what happens as capital R approaches infinity? The inequality still holds, and we take the limit of both sides as capital R approaches infinity. Focusing on the right side of the inequality, we see that 2 pi over 3 can be factored outside of the limit as a constant, and we may now focus on the remaining limit of capital R to the power of A divided by the quantity capital R cubed minus 1. Next, we divide both top and bottom by capital R cubed. This gives us capital R to the power of A minus 3 in the numerator and the quantity of 1 minus capital R to the power of negative 3 in the denominator. Focusing on the numerator, we see that the quantity A minus 3 is negative in this context because the variable A is less than 3 and greater than 0. This causes the term in the numerator to approach 0 as capital R approaches infinity. Similar logic leads to the conclusion that capital R to the power of negative 3 also approaches 0, leaving us with a positive 1 in the denominator. Thus, the limit as capital R approaches infinity of 2 pi over 3 times capital R to the power of A divided by the quantity capital R cubed minus 1 tends to 0. Inserting this value for the right-hand side of the aforementioned inequality shows us that the limit as capital R approaches 0 of the absolute value of the capital gamma integral is less than or equal to 0. Next, we can substitute an equal sign for the inequality because an absolute value cannot, by definition, be less than 0 for any quantity inside of the absolute value signs. Finally, we can say that the capital gamma integral itself is equal to 0. This is because an absolute value can only be 0 when the quantity inside of the absolute value is 0. It seems like a lot of sources showing the evaluation of what I will refer to as this family of integral tend to gloss over the part that I just covered. I've seen both textbooks and videos on YouTube where an infinitely expanding arc is being followed for a path integral, and it's just dubbed as being equal to 0 with no further explanation. I've always found this frustrating, so I had to dig into the details here. I won't be giving examples of who or what YouTuber or what textbook ignored what and where because I don't want to be in the middle of a flame war. Moving on. To the path, little gamma. I wasn't sure we'd get this far. So, To recap some details from earlier in the video, the path little gamma begins at a point in the second quadrant denoted by capital R times e to the power of 2I pi divided by 3. This point falls, of course, on a line that forms an angle of 2 pi over 3, or 120 degrees, with the positive x-axis. The path little gamma ends at the origin and follows a straight line from the end of the path capital gamma and the origin of the complex plane. Along the path little gamma, we will represent the variable z as k times e to the power of 2I pi over 3. Along this path, the variable k shifts between the values of capital R and 0. If we take the derivative of z with respect to k, we find that the derivative has a constant value of e to the power of 2I pi over 3. If we take the formula for the first derivative and multiply both sides by dk, then we have a representation for dz in terms of the variable k. Taking the aforementioned formula for z in terms of k and dividing both sides by e to the power of 2I pi over 3 gives us a formula for the variable k in terms of z. From here we can make substitutions into the path integral for little gamma. Updating the bounds of integration via the formula for k in terms of z gives us an integral that flows from capital R to 0. We then make similar substitutions for z and dz. The result, which we will simplify momentarily, is an integral of a single variable k. In the numerator, we start by distributing the exponent a minus 1 across k and the exponent on the right. In the denominator, we distribute a 3 in the exponent across ak and an exponent in the second term. A set of brackets now appear around the exponential term in our representation of dz in terms of dk. The second term in the numerator has no k dependence, so it can be quickly pulled outside of the integral. This is also the case with the bracketed term originally associated with dz and dk. In the denominator, the second term has a set of 3's that cancel inside of an exponential. The only multiple of k cubed that remains is e to the power of 2I pi. This term is equal to 1 and can be crossed out. Breaking down the exponential terms outside of the integral reveals that the solo remaining term is e to the power of 2I pi a over 3. It now falls with us to solve the integral of k to the power of a minus 1 quantity divided by 1 plus k cubed dk from capital R to 0. Reversing the bounds of integration makes the integral a little easier to work with, at least for me, and we factor out a minus sign before combining it with e to the power of 2 pi ai over 3 in front of the integral. So what happens as the value of capital R approaches infinity? Well, the variable capital R only appears in one place in our representation of the little gamma path integral, and that's the upper bound of integration. So it's legal for us to drop the limit and substitute infinity for capital R, making our integral an improper one. Hopefully you see where I'm going with this. If not, it will become clear momentarily. The variable k is, at this point, somewhat arbitrary. We can call it anything, including x if we want. This should make it obvious that the improper integral, aside from the multiple of negative e to the power of 2 pi ai over 3, is identical to the real improper integral that we've been looking for all along, and we can just call it capital I. The path alpha extends from the origin out to capital R on the positive x-axis. The variable z in the complex plane can be represented as x, since there is no imaginary component, and dz is equal to dx here for our purposes. This leaves us with a real integral from 0 to capital R. As with the previous two portions of our closed path in the complex plane, we will explore the limit of this integral as capital R approaches infinity. No surprise, it works out to the integral that we came here looking for, and unlike the path of lowercase gamma, the result for the path integral alpha has no multiplicative factors. A brief recap is in order. We have shown that the path integral uppercase gamma is equal to 0, that the integral lowercase gamma is equal to minus capital I times negative e to the power of 2 pi ai over 3, and that the path integral alpha is equal to capital I. Capital I, of course, denotes the real improper integral that we are looking for. We should also take a second look at our formula for the closed contour, its constituent parts, and its relation to the residue at point e to the power of I pi over 3. If we insert our values for the three path integrals and the aforementioned residue, we now have an equation that we can use to solve for capital I. So let's hurry up and solve it. On the left-hand side, we consolidate the factors of capital I and place them inside of parentheses. On the right, we combine 2 pi I and 1/3 into a single multiple of the exponential. Going back to the left-hand side, we see that the exponent in the first term inside of the parentheses can be cut in half. This allows us to factor e to the power of 2 pi ai over 3 into two separate terms, both equal to e to the power of pi ai over 3. The second term inside of the parentheses, in spite of just being 1, can be factored into basically anything as long as the exponents add up to 0. So we factor 1 into e to the power of pi ai over 3 and e to the power of negative pi ai over 3. On the right-hand side, the term e to the power of I pi times a over 3 minus 1 can be broken into two separate exponential terms. The second term, e to the power of negative I pi, reduces to a negative 1. We now have terms on both sides of the equation, 2 on the left and 1 on the right, that are equal to e to the power of pi ai over 3. These terms cancel, and we are left with two complex exponential terms on the left, as well as minus 2 pi I over 3 on the right. In order to simplify the remaining exponential terms on the left, we employ Euler's relation. This allows us to express the left-hand side of the equation as sine and cosine terms. We first distribute the negative sign in front of the first set of brackets. Next, we focus on the two minus signs contained within the arguments of the latter two trigonometric functions. In the case of cosine, it's an even function. Cosine of negative theta is equal to cosine of theta, and we can convert it to a plus sign. The sine function, on the other hand, is an odd function where sine of negative theta is equal to the negative sine of theta. So what we can do is pull the minus sign outside of the argument and put it in front of the sine function itself. On the left-hand side, the cosine functions in the first bracket cancel each other out, while the negative sine functions combine. The result is negative 2i times the aforementioned sine function times capital I equal to minus 2 pi I over 3. The term negative 2i factors out of both sides, and we are left with the sine of pi a over 3 times capital I equal to pi over 3. Cross-multiplying by 1 over sine pi a over 3 leaves us with capital I equal to pi over 3 times cosecant of pi a over 3. Capital I is equal to the integral that we came here looking for. Thus, the integral of x to the power of a minus 1 over 1 plus x cubed from 0 to infinity is equal to pi over 3 times the cosecant of pi a over 3 for values of a less than 3 but greater than 0. I think that's a wrap.
So I want to take a second to talk about where the channel may be going. I will start off by saying that I have no intention for Pentagram Prime to become an AI slop channel. However, times are changing, and I thought it important to point out that this video that for a bunch of reasons took me 2 years to make, in some respects might be able to be thrown together with about a day's work in an appropriately equipped lab with AI software, maybe even um, open source stuff. It's really not my wheelhouse. I am not here to go ahead and talk about software engineering or AI. I'm just saying this is what I was able to cobble together um, with a simple prompt on Google. Um, Now, admittedly, if you just type in the integral, you're going to get, you know, you're going to get something involving, I think we got it down here. Uh, no, so, yeah, the beta function. Um, I never did anything with the beta function, which you would know if you've gotten this far in the video. Um, but, if I just simply type via residue theorem, well, next thing you know, we've got the, it's giving you techniques for pulling up the residues themselves. And sorry, I did not script this section, so it's a little bit freestyle. But we've got locating the poles here. Um, I wasn't too happy with the section on the contour because it is admittedly telling you to use what appears to be. Actually, this one might work, the semicircular. I thought it was going to be a. Nope, yep, it's listing a keyhole contour, and gotta say, uh, employing keyhole contour on this problem is what wasted a bunch of my time in the first place. So don't do that. But um, here are those. Here are the residues, and I think this is where everything gets summed up. Yeah. So it's not totally. It's not comprehensive. I don't see anything in here on how to make those contours go to zero, which I spent quite a bit of time on in this video. But it shows where, for lack of a better term, the internet is going. And we're just going to see what happens when we bring up a deeper dive here. Um, I'm just kind of skimming over this as I watch. Um, it's way more comprehensive than anything I recall having access to as of 2 or 3 years ago. Um, I hope going forward there is still a reason for me to make these videos. Anyway, I'm hopeful that academia is not completely dead, at least not yet. Till next time, it's Pentagram Prime signing off.